Greetings, everybody. Learning as a hobby here. I wanted to continue with my series on Charles Platt's Make Electronics. If you have been tuning in last week, you may remember that we did experiment one and two, or maybe I should say half of experiment one and all of experiment two we did last week. And we are using, I have some resistors on the case right now, so I can't show it to you, but we're using the material that comes in the project kit made specifically for Charles Platt's book, put out by Protect Trader. They are a sponsor of the channel, and just full disclosure, they did give me the kit for free for advertising purposes. But I do want to say something about that. Last time, remember when we did, well, I don't know if you saw the video. I said I had an issue with experiment one because the multimeter wasn't able to pick up the resistance of my skin. But having talked to Protect Trader, they mentioned what I can do to try and fix the problem. Also, they wanted me to mention that they do fully support the kit. So if you're missing anything, or if there's any issues with one of the elements of the kit or something, you can contact them through their website. I'll show you the link in a second, and they'll make it right. So, but they'll also give you advice. So if you have some issue with one of the experiments and you don't know what's happening, you can either contact Charles Platt. He has his email address in the book, or you can talk to Protect Trader if it's something to do with the kit. So, but having said that, I did, take their advice on what to do to address the issue that I was having with the experiment one, and I want to show you that actually their advice did help. And actually, I it must have slipped my mind or something. Maybe I just because I didn't read through the section of the book, maybe I just forgot that he mentioned this. But Charles Platt does mention the same advice that Protect Trader gave me, which was that if the test leads don't measure your resistance of your skin or your tongue, sometimes what happens is the probes that come from the factory have a little bit of a film on them, and if you wash them with some dish soap and then use a mildly abrasive some kind of mildly abrasive thing to rub on there, not too abrasive because you'll damage the test leads. Actually, Charles Platt recommends using toothpaste, which is what I did. And if you do that, it will remove the film on the test leads, and then it should pick up the resistance then. So let me just show you that it does work. It's kind of kind of hot in my living room, so you should be able to see it. If maybe I can test the resistance of my sweaty forehead here. So let's see if it actually picks it up. There you go. So it is very like kind of like all over the place when I do it. So I don't know how precise it is because it is a very high resistance. Let me see if I can get a better measurement. It's usually somewhere when I do it, somewhere between like four and five or six even 100 kilo ohms, which is what I'm getting here. So, but like I said, it doesn't seem to be very precise for those high levels of resistance, but it does work. So I just wanted to mention that. And then also, real quick before we get into experiment three, I wanted to show you the website for a Protect Trader, because in the last video their website was not available because they were doing maintenance on the website. So this is the actual website if you're curious. And just like I did in the last couple of videos, I will put the links to the the Protect Trader website down below in the description bar, and also the link to my Amazon affiliate account for the book if you want to pick up yourself a copy of both. So here, just looking at the website, you can see that there's right at the top, there's the Make Electronics Third Edition kit that we're working through, and there's the Make Radio Experiment a component kit that I want to do eventually, and hopefully they'll send me a production copy of that, because I'd like to work through that book at some point too. But if you click on this, for example, on the third edition Make Electronics kit. Then they have it here. Remember that there is uh there's the kit that I have, which is like the first two, allows you to do the first two chapters of the book, and then there's the bigger kit that allows you to do all of them. So I'm hoping that we'll be able to do all of the experiments. But right now we're working through chapter 1 and chapter 2 using this Protect Trader kit. One thing I will mention is I think it looks like it's slightly cheaper if you buy the kits off of the website. So I don't know, you might want to look through the website and see. They do have an Amazon account page also, so maybe I'll link that down below too. But you might want to see which one is better for you to shop on, whether it's the actual website or Amazon. Okay. So that's that. The other thing I wanted to mention real quick is that oh, sorry, I don't want to move away from the website yet. If you go to if you want to contact them for any reason, like let's say you buy the kit and you're having issues with one of the components, you can contact them by just going here to contact us, and you can send them a message and they'll get back to you. So that's Protect Trader's website. Anyway, one other thing I want to talk about before I get to the experiment is that I've been having some issues with DCAC Lab. Um, I contacted their help department or whatever, and they seemed to have fixed it for a little while, but now I'm having trouble with it again. And I had at this point when I'm making this video, it's not been resolved yet. So I'm not going to be using DCAC Lab, at least for this video, just because, like I said, I'm having some issues with it. So just be aware of that. Okay, so now we can get to the experiment. If I could, let me see, stop my screen share. And let me change the angle of the camera. Okay, so real quick recap of what we did last time. We learned about how to test resistance with our multimeter, how to set it up and everything, what all the symbols mean on the multimeter dial here. And then we made a circuit, which I still have set up here. Actually, not exactly how I left it. I changed the resistor here from the 1.5 kilo ohm resistor to 470 ohms because that's what we're going to be starting with in experiment 3. But other than that, it's the same exact circuit that we left off on in experiment 2. In experiment 2, we talked about again, we set up the circuit, and then we learned how to test current with our multimeter. And that was basically it. We talked about some of the history. We talked about ampere, and I think we talked about, who do we talk about in the first chapter? Sorry, the first experiment. Let me just double check. I forget who it was. Oh, we talked about George Simon Ohm in chapter 1, and not in chapter 1, in experiment 1. And in experiment 2, we talked about ampere. We talked about Andre Marie Ampere. And there's another little historical tidbit in experiment 3. I think there's gonna be one in every experiment, which is kind of fun. So let me actually let me just make sure that we talked about everything that we did last time. We talked about measuring current. Yeah, that's basically it. We learned how to use the multimeter to test the current in our circuit. Okay, so what do we need for experiment 3? We need our 9-volt battery. I have everything on the desk here except for the resistors I have on the side here. So we need the 9-volt battery still. We need a 470 ohm resistor, which I already have hooked up in the circuit. We need a 1 kilo ohm resistor, which I have on the side. We need a 1.5 kilo ohm resistor, which I have on the side, a 2.2 kilo ohm resistor, which I have on the side, and a 3.3 kilo ohm resistor, again, which I have on the side. We need our generic red LED, which I have in the circuit already. We need our test leads. So we need the red and black one, and I have another yellow one on the side that we'll use momentarily. And then we need our multimeter. So that's all the equipment that we need. We're going to look at voltages mainly in this experiment. So we're going to learn how to test voltages and how to find voltage drops across resistors and so on. And then we're going to learn about Ohm's law. Okay, so let me start at the beginning. Actually, let me move this out of the way so you can see the book while I'm reading it. Okay, so the first section is in experiment 3 is labeled potential differences. Because your meter will be measuring volts now, it won't be inserted in the circuit anymore. The circuit should look like figure 3.1, which hopefully you can see that in the book here. Um, and the schematic is shown in figure 3.2. So yes, the schematic drawn over here. You're going to measure voltage. So remove the red meter lead from the milliohm socket. In our multimeter, remember that the milliohm socket is actually the same socket as the voltage and the ohm socket, so we don't have to move it for hours. But if you have a separate socket for milliohms, move it back to the volts and ohm socket. Set the dial on your meter to measure up to 20 volts DC or just volts DC if your meter does auto ranging. See figure 3 and figure 3.4. So they're just showing the setting here. Our meter that we have through the ProCheck Trader kit is actually a manual multimeter, not an auto ranging multimeter. If you have a more expensive multimeter, then some of those are auto ranging. So, figure out how to do it on your particular multimeter. Um, Now you can use the meter to check the voltage between any 2 points in the circuit. The meter has very high resistance when it's set to measure volts, so hardly any current passes through it. You can even check the voltage between terminals of the battery, as in figure 3.5 on the next page, and the meter won't be damaged. Make a note of the voltage that you find. Let's do that real quick, and then I'll continue reading what he has written here. Okay, so here's our multimeter and here's our circuit, just to remind you of what this circuit does in case you didn't see the previous videos, which you should go back and look at, because the experiments do build on each other, so that they're sort of like each experiment is a stepping stone to the next one. So you want to watch them in order. Okay, so here this circuit lights up this LED, if you remember. Okay, and this again, this is the 470 ohm resistor that I have attached here. So I want to start by measuring the voltage of my battery. And to do that, he says, turn your multimeter to 20 volts DC. On my multimeter, I don't know if this will show up in the camera, but my multimeter has the blue range over here is for DC voltage, and the section over here is for AC voltage. So I'm going to turn it to 20 volts DC. So that's this setting here on my particular multimeter. Okay, and then we can use this to test the voltage of our battery. Um, so let's actually, I think, let me test it to see. You know what? Just to be safe, I'm going to connect the circuit together because I don't remember. Whoops. I don't remember if the circuit has to be completed for the multimeter to register the voltage. So let me connect this up just to be safe. Okay, so that's hopefully you can see the LED is lit here. Okay, so let's test the voltage of our DC battery. Now make sure that you connect the red to the red and the black to the black. Remember, black should always be in the negative side and red should be in the positive side. So, and actually, let me turn the multimeter so you can see the reading when I test this. All right, so it looks like 9 point, maybe let's say 9.5 volts. Um, okay, so that's the voltage of our battery, and let me disconnect this so we can see what else he wants us to do. So I will actually mark down the voltage that we just recorded. I think I'm going to do that on Desmos just so I can easily keep track of things. So let me bring up Desmos. All right, and here actually I had recorded the values that I got for this experiment previously, but something happened in the middle of my recording of this experiment previously, so I'm gonna just redo the numbers. So here we got for our battery, it was 9.5, I think we said. All right, so our battery's 9.5 volts. So here I'm rounding up. Okay, let's get back to the book. All right, and see what to do next. Okay, when you measure voltage, the meter must not be inserted into the circuit. It sits outside the circuit like an observer at a sporting event keeping score. Right. Remember, when you test current, the meter has to be inside the circuit. But for voltage, you don't want that. If you put the meter probes across the resistor, as in figure 3.6, now you're finding out how much voltage drop the resistor causes in the circuit. Make a note of it. You can do the same thing with the LED. Before we do anything else, let's actually take those measurements and then write them on Desmos so we have them logged. All right, so reconnecting the circuit here. And we'll test the voltages for each part of this circuit. So we already know we already know that the voltage of the battery is 9.5. Let me see if I could move this around a little bit so it's more convenient. I'm gonna have to find, I think, a better surface to do this stuff on in the future, just so things aren't so crowded. But for right now, this is what I got. Okay, so let me see if I can get things to work like this. Okay, so we want to measure the voltage now across the resistor and then also across the LED. So again, I'll go to 20 volts, and I will test. Actually, I want this way so you can see, and I'll test the voltage across the resistor. Right, looks like 7.4, let's say, rounding up, and then let's test the resistance around the LED. If I could, oops, it's kind of hard to, maybe if I put it on the alligator clips. So here looks like 2.1. So what was it? 7 point. Sorry. It's like 7.3 and 2. So 7.3 across the resistor and like 2-ish across the resistor. So let me again unhook this and let me write those measurements down. Okay, so we said 7.5 volts across the resistor. Sorry, I don't know. It's hard for me to see the keyboard because there's a shadow on the keyboard. 7.5. I'm not sure why it's not giving me the decimal here. Oh, there it is. 7.5. Okay. 7.5 volts across. I'll just say maybe because Desmos won't let me write, sentences out here. Let's say 7.5 volts resistor. Right. And then we had two. Oh, wasn't set. No, it was 7. 7.3, I think we had, right? 7.3. And then across the LED, it was 2 volts, I think. Okay, so now we have those measurements logged. Notice that the voltage across the LED and the resistor almost adds up to the voltage of the battery. And he'll mention this later on. This is actually um, uh, what would be the word? This is demonstrating Kirchhoff's law, I think it's called. There's actually two of them. One is about current and one is about voltage. So what this is showing is that um, the voltages across, a circuit have to sort of sum to zero, right? So the voltage across the resistor and across the LED should add up to the voltage of the battery. Okay, that's called Kirchhoff's law. So let's go back to the book. All right, and see what it says. All right, the schematic in figure 3.7 shows the numbers I obtained when I tried this rounded to one decimal place. Your numbers won't be exactly the same as mine because my meter, my resistor, my battery won't be exactly the same as yours. They should be similar though. So he got measurements of 7.2, 1.9, and 9.1 volts for the battery. So again, notice 7.2 plus 1.9 actually adds up to 9.1. Notice that when you add up the voltage drops across the components, the total is about the same as the voltage supplied by the battery. The components take as much as the battery provides because there's nowhere else for the voltage to be lost except through the meter, which only takes a tiny amount when it's measuring voltage. Here are some things to remember when measuring voltage. The circuit must be powered up. The meter is set to measure volts. The meter is outside the circuit. Because the voltage is like pressure, you always measure it between 2 points, one of which has more voltage relative to the other. This is often called the potential difference between them. And then finally, if you connect the meter the wrong way around, it still makes a measurement, but you see a minus sign on the display. The voltage across the LED is known as its forward voltage, and the data sheet in figure 213 suggested a typical value between 2.1 volts and 2.6 volts. So the circuit is just below the low end of the range. For an LED, what the data sheet really means is that if you apply pressure between 2.1 and 2.6 volts, then the LED will satisfy the manufacturer's specification, especially regarding the amount of light it produces. Okay, and then he has something here about volt basics, which I'll skip. It's just about, what does the prefix milli mean when you're talking about volts, etc. It's just the metric prefixes that hopefully you are aware of. Okay, then he has a historical um, note here on the inventor of the battery. Let's read this. And I'm actually excited because I looked a little bit forward in the book, and we do actually get to construct a homemade battery, at the end of chapter 1. So keep an eye out for that. That's going to be a fun experiment. Anyway, let me read about Alessandro Volta. Alessandro Volta, shown in figure 3.9 in the next page, was born in Italy in 1745, long before science was broken up into specialties. After studying chemistry, the discovery of methane in 1776, he discovered uh, the molecule, I guess, methane, in 1776. He became a professor of physics and developed an interest in the so-called galvanic response, whereby a frog's leg will twitch in response to a jolt of electricity. This is October, by the way. That type of experiment also is what influenced Mary Shelley in writing Frankenstein, by the way. Okay, continuing. Using a wine glass full of salt water, Volta demonstrated that the chemical reaction between two electrodes, one made of copper, the other of zinc, will generate a steady electric current. In 1800, he refined his apparatus by stacking more plates of copper and zinc, separated by cardboard soaked in salt and water. This voltaic pile was the first electric battery. Imagine living in the days when you could make a major discovery about electricity using just a couple of metal plates, salt water, and cardboard. Okay, so that's Alessandro Volta. All right, the next section is titled Voltage and Amperage. I think I'm going to skip this. Let me see if there's anything actually that I do have to mention in it. Maybe I should read it just in case people are not familiar with this concept. Um, so voltage is like the way I've just heard it described. Well, Charles Platt describes it here as like pressure. So it's you apply pressure to get the current um, to get a higher current, which you can think of analogously as like the flow of water through a hole in a container or something. And the resistance would be the size of the hole. And if you add more water into the container, then obviously that's more gives more pressure to the water that's coming out of the hole, which will make the flow greater, which is analogous to current and so on. So voltage is analogous to pressure here. I've also heard it related to potential energy, like when you roll a cart up a hill, it has some potential energy that you can transform into kinetic energy by letting it roll down the hill. So same type of thing. Voltage would be like potential energy. Let me read what he says here, though, because he knows more about this than I do. You saw that if you decrease a resistance, more current flows. What if you increase the voltage while keeping the resistance the same? Do you think this is another way to push more current through? Yes, that's what happens. And the best way to visualize it is by thinking of electricity as behaving like water. In fact, in the early history of science, some researchers did actually think that electricity was a kind of fluid because the flow of electrons behave that way. In figure 310, the height of the water in the cylinder relative to the hole will create water pressure. The rate of flow will be similar to amperage, while the diameter of the hole is similar to resistance. When you add more water to the tank, you create more pressure, as in figure 311. Hopefully, you guys can see the pictures here. If the hole in the cylinder is still the same size, the increase in pressure will create an increase in flow. Think of voltage as pressure. It's measured between 2 points. Think of amperes or amps as the rate of flow, properly known as current. Think of resistance as limiting the flow. In figure 312, you can see another way of looking at the situation. He has a picture here. I don't know if you can see this in the camera, but there is a little kid stepping on a hose, which is like resistance, and the faucet is like the voltage, and then uh, the guy that has the head of the hose is labeled reduced flow. All right. Now I want to find out exactly how voltage, current, and resistance are related to each other. And fortunately, this can be discovered quite easily. I'm going to skip the next section because it's just a sort of quick, basic mathematics interlude. And if you're a viewer of this channel, I'm sure this stuff is like old hat for you. So I'm just going to skip it. But if you have the book, you obviously you can read through it. But I'm going to skip that here and go to the next section, which says it's the law. The purpose of this experiment is to make 4 measurements and then reach a conclusion about the way that electricity works. This is how science is done. First, you need some data, and then maybe you can use it to draw a conclusion. All right, disconnect your components and set aside the LED. You won't need it now. You'll need the 4 resistors with values 1K, 1.5K, 2.2K, and 3.3K. That refers to ohms, by the way. Check the voltage of your battery as in figure 313. It's okay to do this when the meter is set to measure voltage because the meter has such a high resistance. This protects it from too much current. Never do this with the meter set to milliamps as you can blow the fuse in the meter. Write down the value that you find. Okay, we'll do that in a second. Or actually, why not? Let's do it now. Let's not just this way we don't forget about things. So, okay, I'm going to disconnect all of this stuff. And he says we can put away the LED. I'll just put this on the side for now. And I'll put this resistor on the side too, because we're not going to use this resistor. All right, and let me just make some room here. All right, so he wants us to test the voltage of the battery again. right? So it should be pretty close to what we measured before. Here I get actually like 9.8 almost if I round up. So actually measurement here is a little bit higher. Obviously these things are not completely 100% accurate because which is true of any measurement, but so it looks like we get if we round up 9.8, we could say between 9.7 9.8 volts. Okay, this is basically a brand new battery, so that shouldn't be surprising. Okay, let's see where we left off. Check the voltage of your battery. We just read that. Okay. Now move the red meter lead to the milliamp socket if your meter has one. I don't have to move it because it's the same socket. And set the meter to measure up to 20 milliamps or 200 milliamps. If the range doesn't go as low as 20 milliamps, I want you to make 4 measurements as suggested in figure 314, which shows that the values that I obtained rounded to 2 digits. Notice I have included the actual voltage from my 9-volt battery. It was 9.6 volts because it was a brand new battery. We got around that value too, like 9.7, 9.8. Next, I copied the values into a table as shown in figure 315. For the last column in the table, I used my calculator to multiply the preceding numbers for milliamps and kiloohms. You can do the same with your values. Once again, I rounded mine to 1 decimal place. Okay, let's actually do this measurement now, and then I'll continue reading here. And actually, before I even do the measurement, let me just write down again what we got for the measurement that we got for our battery because it was slightly different than we got when we had the circuit hooked up. Okay, so I'm going to say roughly 9.7. All right, 9.7 volts. Okay, and now we're going to do our measurements. So what we're going to do, let me just show you this chart so you can hopefully it'll show up on the camera. These are the 4 measurements he wants us. Oh, actually, let me stop the screen share so you can see this better. Okay, so these are the 4 measurements he wants us to make. And hopefully that's visible to you guys on the camera. So first thing we'll start with the lower the uh the lowest value resistor, and we'll move up in resistance. So we'll start with the 1 kilo ohm resistor, then we'll do 1.5K, then 2.2K, and then 3.3K. So let's actually set that up. All right, I need my leads here. I guess I could have left this hooked up before, but the covers on these on these alligator leads sometimes are slippery. It's hard to get a grip on them. There we go. Okay, let's start with the 1K resistor, right, which I have here. Again, you can tell the different resistors by the color coding on the body of the resistor. Okay, so let's hook this up. Oops. I'm going to use my yellow lead here. Okay, and now I'm going to hook this up to my test leads on my multimeter. Let me see if I can move this out of the way so I can make more space. And I want you guys to be able to see, whoops, I want you guys to be able to see the numbers on the multimeter. So he says, what was the setting? I think he said 200 milliamps. Let me just double check. All right, we want actually 20 milliamps, right? Which on my meter is over here. Okay, and now I'm gonna hook up my multimeter into the circuit. Okay, by using my alligator clips. So clip this here, clip this here. Okay, and hopefully you guys can see that number here. It looks like I get 9.6. So I'm going to mark that down. Oop, I'm going to mark that down on Desmos so I don't forget it. All right, so that's 9.6 milliamps. Right, and then we'll move on to the next resistor. So let me unhook this one. And then we'll go to the next highest one, which is 1.5 kiloohms. So hook that one in. Again, if I could get the alligator clip to cooperate with me. All right, there we go. And where'd my lead go? Here it is. Okay, and now just keep an eye on the multimeter here. I'm going to test this one. All right, here we get, it looks like 6.4. Let's mark that down so we don't forget. All right, 6.4 milliamps for the 1.5 ohm resistor. Sorry, the 1.5K resistor. And now let's move to the next highest resistor. All right, this one is 2.2 kiloohms. Again, hopefully you can see the difference. Actually, let me stop my screen share. So hopefully you can, again, see the different colors on the, I don't know if it'll focus on it, but it has different color codings on it. All right, and let's test this one. Again, keep an eye on the multimeter. All right, this one gives me 4.4 milliamps. So let me mark that one. Right, and last one, 3.3 kiloohms. Right, we'll put this one into the circuit. Oh, let me stop my screen share. And I just want to make sure that the audio is still working. Okay. Come on, Mr. Alligator. Come on. I don't know why this is so so difficult. Ah, there it goes. Okay. All right, that's the 3.3K. Now again, let's measure the amps. So keep an eye on the meter. This one gives like 2.9. So we'll mark that down. And I'm going to turn my multimeter off. And I'm going to put this resistor away just so I don't forget. Okay, this is in milliamps, by the way. All right, and now we can see what Mr. Platt wants us to do next. I'm going to leave the battery hooked up because we're going to use it again in a few minutes. Okay, now he's going to talk about Ohm's law. Okay, so he says, um, next, I copied the values into a table as shown in figure 315. For the last column in the table, I used my calculator to multiply the preceding numbers for milliamps and kiloohms. You can do the same with your values. Once again, I rounded mine to one decimal place. Do you notice anything odd about the table? The values in the last column are all very similar and they are all close to the voltage of the battery. Let's actually show that with our numbers. He has his numbers that he measured, but let's do it with our numbers as well. Now I'm going to actually change the I'm going to change the units here to be more in line with the way that Ohm's law is stated. So instead of using milliamps, I want to use amps, and instead of using kiloohms, I want to use ohms. So for the first measurement, we had 9.6 milliamps. Let me just move the microphone here a little bit. So we have 9.6 milliamps, which is the same thing as 0.0096 amps. And the resistor for that one was 1 kiloohm, or in other words, 1,000 ohms. And if you multiply those two things together, notice you get 9.6, which was very close to what we had for the measurement of our battery. So here, 9.7 volts was our battery. Here we have 9.6, which is pretty close. All right. For the second one, we had was it 6.4? Yeah, 6.4 milliamps. But again, I'll turn that into amps. So 0.0064. And this one was 1.5 kilo ohms, or in other words, 1,500 ohms. Right. And again, notice we get 9.6, again, close to the value of our battery voltage. Okay. The third number was 4.4 milliamps, or 0.0044 times. That one was 2.2 kiloohms, or in other words, 2,200 ohms. Oops, did I? Oh, there it goes. Sorry, 9.68. So again, very close to the value of our battery voltage. And then last one was 2.9 milliamps, which is the same thing as 0.0029 amps. And I'm going to multiply that by 3.3 kiloohms, or in other words, 3,300 ohms. Right, we get 9.57. So again, notice that all these numbers here, all these products are very close to each other, and they're also close to the value of the battery voltage that we measured. Okay, and this is due to something called Ohm's law, which he's going to explain here in a second. So let me read what Charles Platt has to say about Ohm's law. Okay, anytime you see a coincidence like this, you have to wonder if there's a pattern. If you were doing serious research, you'd try this experiment many times using many other resistors and different power supplies. To make sure, you would also use a very accurate metering system, but I can tell you the result will be the same every time. It will look like this: voltage equals milliamps times kiloohms, or if you change the units the way that I did in my calculation, you get voltage is equal to amps times ohms, or in other words, voltage is current times resistance, which is called Ohm's law. So suppose I use letter V for volts and the letter R for resistance in ohms and letter I for amps. Why letter I? Because current used to be measured by the effects it induced. This is a complicated topic, but in any electronic formula where you see I, it means current. So V equals I times R. Remember, V must be in volts. I must be in amps and R must be in ohms. This is known as Ohm's law, the most basic formula in electronics. You just discovered it or rediscovered it. Actually, I would take I would say that a little bit differently. I don't know if we discovered it rather than we verified it in a certain number of cases. But in Figure 316, the resistance can consist of one resistor or a whole series of them. And then he talks about format conversion. In other words, you can use Ohm's law to solve either for resistance or voltage or current. And you can use that, for example, to figure out what the resistance of, for example, the LED that we were using is, what the resistance of this LED is. And if you do the calculation, you'll see it's roughly like 300 300 ohms. Yeah, 300 ohms. Just by using, Ohm's law. Okay, so in other words, R is V over I is V over R, and V is I times R. Then he talks about decimal conversion. I'll skip that. Uh, and then this is an interesting section here. Meter participation. I skipped over the exact effect that the meter may have when measuring volts. I mentioned that its resistance is very high, but surely it must have some tiny effect. Yes, it does, which is one reason why I didn't get a consistent result when I multiplied milliamps by kiloohms, but there's nothing you can do about it. I rounded the numbers down to 2 digits because I knew the meter would affect the accuracy of its own measurements. This doesn't sound very satisfactory, but as a general rule in all aspects of science, the process of measuring something tends to affect the value that you're trying to measure. Okay, and then he talks about how to measure resistances when you have resistors set up in series and in parallel. So this is important to know. So let me just talk about this, and we'll talk about cleanup recycling, and then I want to show you a couple last things before I close out this experiment video. In the simple circuit that you have built so far, electricity ran through one component after another. The components were in series. When you have two resistances in series, you add their values to get the total resistance. So for example, if you have a 1 kilo ohm resistor in series with a 1.5 kilo ohm resistor, the total resistance from the two resistors will be 2.5 kiloohms. All right, what if you put two equal resistors beside each other, as in Figure 318? Well, now the electricity has two paths to take. So if the resistors are of equal value, the overall resistance is divided by 2. We now say that the resistors are in parallel. What if the resistors are not equal in value? If they are in series, you add their values as before, but if they are in parallel, it's a bit trickier. You could investigate this by combining various resistors and using your meter to measure their resistances. in parallel, but let me make it easier for you. If R1 is the value of one resistor and R2 is the value of another resistor, and they're in parallel, the overall resistance R is found like this. 1 over R equals 1 over R1 plus 1 over R2. That's not very helpful because you want to know R, not 1 divided by R. All right, high school algebra tells you that you can convert the formula like this. 1 over R equals R1 plus R2 divided by R1 plus R2. That's just putting over the LCD. And then take the reciprocal, and you get that the resistance is R1 times R2 divided by R1 plus R2. Did you really need to know this? Well, yes, it can be useful, and I would not be doing my duty if I didn't mention it. I realize that some people don't enjoy algebra very much, so I won't go into any more detail here, but I do have to include a little math in the next experiment, telling you how to figure out the power required by a circuit. That's important. Okay, before I get to cleanup and recycling, I just want to demonstrate that with a couple of examples here. So maybe we'll do one in series and we'll do one in parallel just to show you that um, you get what he suggests there, at least in the cases that we'll look at. So let me take ones that have easy values to use. So this is 1 kilo ohm, and this is 1.5 kilo ohm. Let's connect these in series and see what the total resistance is by using our multimeter. So first I'll connect these together in series. All right, so now let me just make this a little bit more secure. Okay, let me connect this to the multimeter. And here we're measuring resistance, so we have to use the settings down here. And our prediction is that so it's a 1 kilo ohm resistor and a 1.5 kilo ohm resistor. If we have them hooked up in series like this, we should end up with a total resistance of 2.5 kilo ohms. So I'll use the 20 kilo ohm setting on my multimeter. Right, and let me put this like that so you can see it. And let's test the resistance, the total resistance that we get. And lo and behold, we get 2.5, well, approximately 2.5 kiloohms. Okay, that's in series. So that checks out. At least in that example, it checks out. Let's check what happens if we connect these in parallel now. Sorry, that was series. Let's check parallel now. So here I'll connect these together. Whoops. I can get the alligator clip to hold both of them. This is like the hardest part of the whole thing is getting these alligator clips to open up. All right, let's see if I can get this to work out here. Come on. Right, and then the other end I'll hook up as well. Actually, let me do it with another clip here. Shoot. Sorry, just bear with me, guys. You know what? What if I try this? Because these clips are not wanting to cooperate with me. Maybe I can just touch them both to the probes here. Let's see if this will. Whoop. I don't know if this is going to work, but yeah, I'm gonna have to. Sorry, I'm gonna have to use the clips. This is gonna be kind of a pain in the butt to clip these together, but all right. Will this stay? This one is not locked in there. Okay, hopefully this will work out. Let's see now. Okay, so hooking these up and seeing what the total resistance is. Okay, here I get, let's see, let it settle down. Looks like 0.6 or maybe 0.59. I'll say 0.6. And that is because they're in parallel. Let's check the formula. I'm just going to disconnect these. Let's check the formula to see, make sure that it works. I'll check it on, whoops. I'll check it on Desmos. Okay, so the formula says that the resistance should be okay. So the formula says this should be um, 600 uh 600 ohms, and we got, what was it, point, I had it on it was 0.6 kiloohms, which is the same thing as yeah, 600 ohms. So it looks like that formula works out as well. Okay, so this is 600 ohms here. And so those formulas work. That those formulas will be useful for us. I also wanted to show you, just so we can, we can use Ohm's law to figure out the resistance of the LED too, and I'll show you where that number came from. So remember, all the way back at the beginning, we measured that the um, across the LED we had a measurement of 2 volts, and we know that the we you know what, we measured the we didn't measure the current, did we? You know what? Uh, should I set it up again with the 1500? Because we know that the current in the, if you use the 1500 milliamp resistor, it ends up giving you a current of um 5.1 milliamps. So actually, maybe we can measure that with, let's just make that circuit again real quick. You guys got time, right? And then measure it and see what we get. This way we can verify that it's 300 ohms, and you can see that the formula works. So okay, let's hook up the LED again. Just bear with me, guys. All right, which one of these was the 1500? Let me check. Right, this is the 1.5, so I'll hook that one up. All right, circuit is complete now. And then now I want to measure the, let's see, I'll do 20 volts. I want to measure the voltage across the LED here. I get like 1.9, and the voltage here 9.5. Okay, going back to Desmos. All right, let's do the calculation. So voltage over resistance should, whoops. Sorry about that. Voltage over current should give us the resistance. So here we have the voltage was what did I say? 1.9 volts divided by the current. We want that in amps, not in milliamps. And it was 5.1 milliamps when we measured it in the last video. So that would be 0.0051 milliamps. Sorry, amps. And if you notice, we get 372.5 roughly ohms for the resistor, which, like I said, it's around 300 ohms for this particular LED using Ohm's law. Okay, so I just wanted to show you that usage of the formula. Let me stop the screen share. I'll talk about the cleanup here, and then I'll end the video, and I'll say goodbye to you guys. Okay, so cleanup and recycling. You won't be using the LED in the next experiment, and the only resistor will be the one rated for 15 ohms. You can store the resistors that you're not using by putting them in little bags or envelopes and writing the value on each. Small containers that people use for beads are a better storage option. I'll have more to say about that in the beginning of section 5. The 9-volt battery should still be good. Okay. So let me stop the screen. Sorry, let me change the camera angle here, and then I'll say goodbye to you guys. All right, so that was experiment 3. Let me know what you guys think down below. In the next video, we'll do experiment 4. And then after that, at the end of chapter 1 is a really fun experiment where you make your own battery. So we'll do the next experiment 4 in the next video. Then the next one will be experiment 5. So let me know, like I said, let me know what you guys think down below. Give Protect Trader their website a peruse to see if there's anything there that you want to pick up. Like I said, the kit that I'm using to go through the experiments in this book is from Protect Trader. Yeah, I'll see you guys in the next one.